Okay, so yesterday we talked about, just kind of introduced you to the parent functions. Today we're going to start talking about transformations, about now how can we take those vanilla parent functions and turn them into, soup them up a little bit, translate them around, stretch them, reflect them, stuff like that. Okay, so overview real quick. So what we're going to do, if p of x, we're going to define that as one of the parent functions. It could be any of those parent functions we talked about yesterday. If we want to start with that plain old function p of x, we can introduce these three numbers. We call them parameters in math, but they're going to be numbers that we're going to use to tweak the function, right? And here's where they're going to go. H is always going to be the number that's being subtracted from x inside the parent function. K is going to be the number that's added to the whole thing outside of the parent function. So just at the end, we're adding this to the whole expression. And A is going to be the number that's being multiplied by the parent function. Those are the three numbers we're going to introduce. We're going to talk about A as being the vertical dilation factor. So that's telling us how much the function is being stretched vertically or compressed vertically. And also, if the function's being flipped over, so it's being reflected, so it's upside down. H represents the horizontal translation. Translation, remember from last year, is just sliding something, right? And K represents the vertical translation, how far we're sliding it vertically, okay? All right, so let's focus on these things a little bit. So how about if we look at, let's explore what happens if we add or subtract something to x inside the function. Let's just see this in action. Okay, so we've got some absolute value functions, what we're going to use as our guinea pig. And look what we're doing here. This is the parent graph, absolute value of x. It's the green graph. Okay, notice that it's got, here, let me change something. Let's do this. Let's step by ones. There we go. So notice that, just like we'd expect, we go over one and up one on our parent graph. We go back one and up one, over two and up two. It's that V shape we're familiar with. That's our absolute value graph. Okay, I'm going to turn on a different function now. The red function, which sits right on top of that, is the function f of x, which is the absolute value of x minus h. And I'm going to be able, I've got this slider here, so I can pick the value that we're subtracting from h. Right now it's 0, so nothing's being done. But look what happens if I drag it over so I'm subtracting 1 from h. What do you think is going to happen if I subtract 1 from h to this thing? Any ideas? Going left 1? Okay, close. I go right 1. Okay, if I subtract 2 from h, I go 2 to the right. What if I subtract negative 1? Then what's going to happen? Then I'm going to go left. Okay, but remember, subtracting a negative looks like addition, doesn't it? Okay, right? So that accomplishes that horizontal translation we were talking about. Okay, now keep that in mind, that h is the number. H tells us how far we're sliding horizontally. If h is equal to 2, then that means we're going 2 to the right. But h is the number that's being subtracted from x. That is confusing to people sometimes. Because if you have something like the absolute value of x minus 2, it just kind of seems like it ought to go left instead of right, but it doesn't. Because that means h is equal to positive 2, right? Okay, so there's that guy. Now let's try. So what's this tell us then? And you can add this to your notes. If we add a number to x inside, we're actually subtracting a negative. And so we're going in the negative direction. We're going left by h units. If we subtract h from x, then we're subtracting a positive value. H is positive, and so we're going to the right. Okay? Everybody get that? Okay, now what happens if now this is different, right? We were subtracting a number from x inside the function. What happens if we add or subtract a number that's outside the function this time? Yeah, it's going to go up or down. You're right. Okay. So again, there's my parent graph. Now here's the new graph. F of x equals the absolute value of x plus k outside. Well, if I add 1 outside the function, yeah, it goes up by 1. If I add 2, it goes up by 2. If I add -1, same as subtracting 1, it goes down. If I subtract 3 or add -3, it goes down by 3. So that one's a little bit easier to wrap your head around, right? So what's this going to do then if I add a number outside the function? It's going up. Yeah. So that means it's going up by k. K is the vertical translation. Subtracting k is the same as adding a negative number, so it's going down. Now notice, see, they work oppositely, don't they? Right? K works like you'd expect. H is the one that's tricky because it's being subtracted from x. That's the one that seems a little bit backwards. Okay. What happens if I do both of these at the same time? What if I subtract a number from x inside the function and add another number outside the function? Yeah, then I'm going to slide horizontally. I'm going to move to the right by h, and I'm going to go up by k. So I get two things at the same time. Okay, give me 1 to 5 on that, everybody. How we doing? Is that good? Okay. Questions, Johnny, on that? You just need a little practice, probably, right? Yeah, we'll get some. We'll go through some examples where you can get some practice. So this takes us back. I don't want to spend a lot of time on this, but the translations are what we call isometric transformations. You might remember that from last year. Iso means same and metric means size. So isometric transformations are the ones that keep the shape the same size as it was before. We're going to translate this year. We're not going to do a lot of other fancy ones, but in the past, you might have done rotations, right? Rotations keep the shape the same shape and size, keep the object the same shape and size. Or you also maybe did some stuff like this, like maybe you did something like flipping it, right? Reflecting it. Reflecting it also, notice it keeps it all the same shape and size. Now, dilations are different. Dilations, if you do a dilation, it keeps it the same. I don't want to do it that way. Hang on a second. I want to do this. Let's go from that corner. If I dilate something, it keeps it the same shape, but different size. Now, we're going to do something even different from that, from what you did last year. We're going to do vertical dilations. Vertical dilations only change the height of the object. They don't change the width. So this is what a vertical dilation does, right? It's either going to stretch it up so everything becomes, like, for example, twice as tall as it was originally, or I could compress it where everything is, for example, only half as tall as it was originally. Okay? All right, so the dilation part. Well, that's what this A is going to do, right? If I multiply a function by A, watch what happens. So there's my parent function, right? I'll turn on f of x, which is all I'm going to do is multiply the parent function by a. Now, what if a is equal to 1? I haven't changed anything, but what if I make a equal to 2? Look what it did. It moved everything up. It moved everything up so all of the points now are exactly twice as high as they used to be, right? Originally with my parent graph, when I went over 1 to the right from the vertex, the height was 1. But now after I dilate it, when I multiply the function by 2, now I go over 1 and the height is 2. You see what's going on? Normally I'd go over 2 and up 2. Now I'm going over 2 and up 4. Okay? Well, what if I make, if A is bigger than 1, I'm stretching it. What if I make A something that's between 0 and 1, like 0.5? What's going to happen if I multiply the function by 0.5? It's okay. The height is the width is always going to stay the same, but what's it going to do vertically? It's going to compress it. Yeah. Now look at all those values. Look at the points on there. If I turn this into zero point 0.5, notice that the points don't move horizontally. They're only being stretched or compressed vertically. So I used to go over 1 and up 1 on my parent graph. Now I'm going to go over 1 and up 1 times 0.5, which is just 0.5, right? I used to go over 4 and up 4. Now I'm going to go, what did I just do? Now I'm going to go over 4 and up my normal amount times 0.5, which, 0.5 times 4 is 2. So now the height on the dilated function is only 2. Everybody see what that does? Okay. So when the absolute value of a, when a is greater than 1, then that's going to stretch the function by a factor of a. Multiply all the heights by a. When a is less than 1, I'm going to compress by a factor of a. Okay, what about this one? What happens if a is negative? Anybody want to take a guess what happens when a is negative? Yeah, it's going to flip it around. Exactly. Let's watch that. So there a is 1. What if I make a negative 1? Well, it did the same thing we did before, only if I multiply the height by a negative, I get a negative outcome, right? Instead of going over 2 and up 2, I'm going to go over 2 and up 2 times a, which is negative 1. 2 times negative 1 is negative 2. So now the instructions are over 2 and up negative 2. It means down 2, right? What if I make a negative 2? What's that going to do? What's that going to accomplish? What's it going to do? Okay, good. Yeah, it's gonna stretch it, but the fact that it's negative means it's gonna open down instead of up, right? So there we go, right? If a is negative 2, now instead of going over 1 and up 1, I'm gonna go over 1 and up 1 times negative 2, so over 1 and down 2. Okay, and of course, if I make a something like negative 1/2, it flips it and compresses it. Now, instead of going over 2 and up 2, I'm going over 2 and up 2 times negative 1/2, which is negative 1. Okay, give me 1 to 5. Does that all make sense? Okay. All right. All right. So reflections reflect across the x-axis. They just flip it upside down. Okay, so what about something like this? If p is the parent function, what are the values of a, b, or a, h, and k here? Remember, a is what's being multiplied out front, right? So what's a going to be? Negative 1/5. Okay, everybody see that? Oops, bad color. Let's pick. Well, actually, I'll pick green. So negative 1/5 is the value of a. What's the value of h going to be? Okay, now is it 8 or negative 8? There's the question. 8. It's positive 8 because look, h is the number that's being subtracted from x. That is tricky. That one always gets people. You see how that one's sort of backwards from what you would expect? Just remember this, remember that h is the number that's being subtracted from x. So whatever the operation is that's connecting x to that number, the sign of h is always going to be the opposite of that, right? So if it's x minus something, then that means h is positive. If it's x plus something, then that means h is negative. Let's get phones away, please. Right? And then k is easy. Don't overthink k. K is just the number that's being added outside. So what's the value of k? Negative 2. Yep. Okay, there we go for our notes. All right, what about this one? Now we're going to get one step trickier. So this time, this is our function that's been transformed, f of x is. I want to know four things here. I want to know what's the vanilla function that we started with, our parent function, and what are the three things that we've done to it? What are the values of the three parameters? On this first example, let's start off with the parameters. Johnny, what's the value of a? 3. Everybody agree? 3 is the number that's being multiplied out front. What's the value, Trenton, of h? 2. Not -2, right? It's 2 because 2 is the number that's being subtracted from x inside the function. And let's see, Mackenzie, what's the value of k? 1. Okay. Now, what's the original function that we started with? What kind of function is this that we transformed with those numbers? So in other words, if we just eliminated all the numbers, what would we be left with, Ben? Absolute value of x. There you go, right? So if I were to just make all the numbers disappear, the vanilla function that we started with would have just been an absolute value function. Everybody get that? So that's telling us what the function looks like, what the graph looks like, what's its shape. And this stuff is telling us what are we doing to it, right? Well, what are we doing to it? What does the h do? What does that mean? H equals 2. Going right by 2. K equals 1 means going up by 1. A equals 3 means, okay, everything's getting stretched by 3, right? Okay. Okay, but take a look at that one for a second. Take a look at that one. That's our next challenge. Okay, Arson, what do you think? What's the parent function this time? If I just eliminate all those numbers, what would we start with? What's the easiest, what's the vanilla function we're starting with? X squared, good. Okay, so we're starting with an x squared and we're doing some stuff to it. Miranda, what's the value of a? Almost. -1/3, right? -1/3. What's the value of h, Malin? -1. Excellent. Good. Not +1, -1. And what's the value of k, Abby? What's being added outside? Say it again. Well, that's part of the parent graph. But is there a number being added outside? So what must it be? 0. Yeah, right. If it's not there and it's being added, doesn't show up, it must be 0. Okay. Good. Okay. Try that one. Everybody, look at that one. Melanie, what's the vanilla function there? What do we start with? Square root of x. Good. What's the value of a? Let's see. Thayton, what's the value of a there? Not 0. What's being multiplied out front if nothing's showing up? It'd be 1, wouldn't it? Now, what if it were 0? 0 times anything is what? 0. So it would have just disappeared. So it's got to be a 1. Good. Okay. What's the value of h, Johnny? -4. Good. What's the value of k? Go ahead, Mackenzie. -7. Good. Okay. Perfect. Okay. Man, you guys are getting this. Okay. This is a tricky one. Yikes. What's the vanilla function there? What's the parent function? What is it? Say it again. Yeah, it's that thing, isn't it? The log. It's a weird one. ln means natural log or log, right? So that's kind of a strange one, right? Okay. What's the value of a, Miranda? 1/4. What's the value of h, Malin? 0. Yeah, nothing's being subtracted from x inside the function. Good. And what's the value of k, Abby? 5. Good. Okay, you guys are getting this. Let's do one more. We get a really tricky one. How about that one? Yikes. That's a tough one. That's a tough one. Arson, can you tell me what the vanilla function is there? What our parent graph is? That's it, 2 to the x. Good, right? Good job. That's a tough one. Okay. What's the value of A then, Melanie? 3. Okay. Trenton, what's the value of H? No. It's 12. Yeah, what's being subtracted from x inside what's inside the function here? The x is in the exponent, right? So in the exponent, 12 is being subtracted from x. And then finally, what's the value of k on that one, Ben? Negative pi. Okay, we got it. Good job. Okay, so what's the order in which we have to do these things? Well, if we were going to follow order of operations, it would tell us we have to do everything in parentheses first. So that would say the first step is we're going to shift horizontally h units, right? Then what would be next by order of operations? Well, there's no exponents. We do multiplication. So then we would have to do the multiplying by a, which means we're going to vertically dilate, right? And then finally, we add or subtract. And so we would finally do the vertical translation of k units. Okay, but the good news is that these transformations are all independent of each other. You can perform them in any order you want to. And so we're going to come up with, just for today, this would be a good ending place for us. We want to come up with the most convenient order to use when we're doing all these transformations at once. Now let's do it once, just following order of operations. Okay, so what are we going to do first here? Let's see. If we're going to follow order of operations, then we got to go inside grouping symbols. So we're going to go 4 to the left. Correct. Good. So we're going 4 left, takes us there, right? Then what? Then we got to multiply by negative 1/2. What's that going to do? Going to flip it and compress it. And when we calculate the heights that are being compressed, we always start at the vertex, right? So instead of going over 2 and up 2, we're going to go over 2 and up 2 times negative 1/2. What's negative 1/2 times 2? Negative 1, right? The 1/2 times 2 gives us a 1. The negative makes it negative. So instead of going over 2 and up 2, I'm going to go over 2 and down 1 from the vertex. Okay. So what's that look like then? That looks like that. So there's the shape. And then the last step would be to add 3, right? So we're going to, adding 3 outside just means I'm going to shift the whole thing up by 3 and we're done. Okay. That's fine. We can follow those steps. But most people find it easier, and that's the way we're going to do it, to do both the translations first and then dilate it. Okay. So let's take an example here, and let's go through an easier. We're going to do the dilations first, the translations first. We can do them at the same time, and then do the dilation. So first of all, what are the values of A, H, and K? We always have to identify what those numbers are because those are telling us what the transformations are going to be. So what's A, everybody? 3. What's H? 5. What's K? Negative 6. Okay, good. So the first thing we're going to do then is we're going to take this guy and we're going to do the translation. So H is 5 means I'm going right 5. K is negative 6 means it's down 6. So let's do both of those at once. Let's take this guy and we're just going to go right by 5 and down by 6. Okay, so there we go. We did the translations. Okay, now A is equal to 3, right? So if A is equal to 3, then from the vertex, normally we would go over 1 and up 1, over 2 and up 2. When we talk about the height of a function from the vertex, you could describe it in different ways. It depends how far you're traveling from the vertex. If we're bumping 1 to the right, then the height is 1 if the normal height is 1. If I bump 2 to the right, then the parent height is 2, etc. We'll always just pick the most convenient one to use, which is usually just over 1 and up 1 for an absolute value function. Okay, A is what we're going to multiply by our normal height. So instead of going over 1 and up 1, we're going to go over 1 and up. Whoops, we're going to go over 1 and up 1 times 3. So we're going to go up to there, right? We're going to stretch that thing up by a factor of 3, right? Everybody see? So that's really what we're trying to accomplish. Over 1 and up 3. And again, that's what it looks like. There's our final answer. Okay, that makes sense? Translated it first to put the vertex where it's supposed to be. Then we do the dilation, and we're done. Okay, let's try one more. All right, so there's our final page of the notes that kind of showed us what we did. This will all be in the PDFs when you want to look at the notes. Okay, what about this guy? So now we've got, it looks like an absolute value function again. Those are, and all those parent graphs we looked at the other day, honestly, the ones we're going to use are, at least at first here, are just going to be absolute value graphs because they're so easy to draw.
Good morning, Buffers. Just a quick reminder, if you have a PE class this week, please go to Warburg Court. Again, all PE classes will be in Warburg Court for the rest of the week. The gold gym is not in use. Thank you.
All right. Good enough. Hey, good job. We'll pick this stuff up tomorrow. I'll put the first assignment up. You can start on it, but we'll wrap this up tomorrow. You get a little bit of work time on it too.